So let us continue with another example. This is example 2.8 from Saadat, a book on power system analysis. Okay, so this problem says a three-phase line has an impedance of 0.4 plus j 2.8 per phase. So this is the three-phase transmission. This is the three-phase system, of course, because the problem says this is a three-phase line. The line feeds to balance. So the keyword is balanced three-phase load that are connected in parallel. Okay, so this is common because the connection of the multiple loads should be in parallel because we need to have equal voltage supplying to each of the load. The first load is absorbing 560.1 kVA, so the S is given. Okay, the S is given, and the power factor of 0.707 power factor lagging. This is the first one, the first load, and the second load absorbs 132 kilowatt at unity power factor. So the two loads are absorbing both active and reactive power, as you can see from the power factor that is given for the load 1, and the load 2 absorb the 132 kilowatt, but at unity power factor, meaning that the Q is 0 for the load 2. The line-to-line voltage at the load end of the line is 3810.5 volts. So basically this is 3.8105 kV. Okay, normally we should work in kilovolt. All right. The problem asks you to determine 3 questions. The first question is the magnitude of the voltage at the sending end of the at the source of end of the line. Okay, source end or sending end. Okay, so this is so this problem is just a little bit different from example 2.7, because the 2.7 gave us the voltage at the supply side, right? And this is the for this problem the voltage at the load premises is given. So you can see that the problem in this subject, it's there are not so many varieties, right? I would say that there are not so many varieties. So the voltage at the load is given, and the problem asks you to compute the load at the source, or either the voltage at the supply is given, and the problem may ask you to compute the voltage at the load. Okay, this is the common pattern. I would say this is a very common pattern for power system. Okay, for both power system 1 and 2. Okay. For the problem B, asks you to compute the real and reactive power loss in the line. Okay, this is just the same as the previous one where we compute the S line. Okay, we will do this one more time with this problem. But the problem, the difference between 2.7 and 2.8 is that the load in 2.7 was the loads were given in terms of impedance. But here, the loads are given in terms of power quantities. Okay, the difference between 2.7 and 2.8, you should note this difference, because 2.7 the loads are given in impedance. Okay, whereby the loads in this problem 2.8, the loads are given in terms of power quantities. So you have to know the steps to handle the 2 different types of the node, but that is very simple, right? So the problem C is the real and reactive power at the sending end. So it's the same pattern of questions. All right. If you still don't, if you still cannot visualize the system, okay, I will try to draw this system for you. Okay, so basically this is the 3 transmission line that is the problem specified, okay, each of which has an impedance of 0.4 plus j 2.7. Okay, these are the 3 lines. Okay, these are the supply. Okay, and this is a voltage at the sending end. So this side is the sending end or source end. Okay, these are the source, and the loads are there are 2 loads basically. The loads are connected in parallel, meaning that this is the load 1. If it is, this is the load 1, and you have load 2, right? So connection in the parallel connection means that the voltage drop across load 1 and load 2 are the same. So what do we need for the load? For the load 1 is the voltage supply, right, in 3 phase. So you need the supply like this. Okay, and these are the connection. So we tap the voltage from phase A, B, and C. For this is A, B, and C. Remember, this is the different side of the line, so the voltage is different. So there is a different nodes, so called A prime, B prime, and the node C prime is right here. Okay. In parallel connection would means that the voltage drop across the load 1 and load 2 are similar. So the load 2, we also need the similar voltage to be fed to this load 2, and also, yeah, this is a phase B and this is phase C. Okay, so these are, you can visualize the connection of this system. And this is the load 1 with 560.1 kVA, 0.707 lacking, and this is 132 kV unity PF. So the way we solve this problem, you have seen from the first example we discussed in this lecture, is that we try to use the power triangle to sum up the load, and we try to find the big equivalent load, right? And the way we do this is pretty straightforward. Okay, we draw the power triangle for load 1. Okay, this is for load 1. So load 1 here, the S is given because this is 560.1 kVA. Okay, and the angle of which is the power angle is arc cosine of 0.707, and this is the 45 degree. It is simple. So 45 degree would means that the cosine and the sine, meaning that these two are equal, right? So the P and Q components are equal, which is the 396.05 kVAr for the Q, and this is the same number for the P, but this is the unit of which is kilowatt. This is for load 1. Okay, for load 1, this is load 1. For the load 2, you can see that the unity power factor is given, so it's represented by the arrow. Okay, 132 not kV but 132 kilowatt. I'm sorry. So this is 132 kilowatt. Okay, you sum up the load for the power for both the 2 loads. Okay, the way we sum up this is that we just sum the real part and the imaginary part. Okay, so after the summation, you would get the S load. I will not draw the total, the resultant power triangle. I think everybody knows, because the reactive part remains 396.05, but the active part is 528.05, because these are the sum of these 2 figures plus J 396.05. The unit of which is kVA, okay, because this is a complex power. So you can also represent this in terms of polar coordinate, or the phasor, which is 660.0704, and angle of 36.87 degree. The unit is kVA, so don't forget to write the unit. Always write the unit, because you will get confused whether it is VA or kVA or MVA. Okay, trust me. Okay, and the power, the given power here, okay, or the load power, this is the total load power. Okay, total load power. Okay, it's just the complex sum of the load 1 and the load 2. So remember, this is the three-phase system. So the summation or the total sum of the complex power here is in the three-phase quantity. So this is three-phase quantity, right? The way we would solve this problem is that, you know, you can refer back to the picture, right? To the circuit diagram. The line-to-line voltage at the load end of the line is 3810.5. If you put this figure, this information onto the circuit diagram, okay, you must be able to put the right to put the numbers into the right position. Okay, so the information given here would mean that this is a voltage at between the load ends of the line. Okay, so the 3810.5 volts, it's at this point between A prime and B prime. All right, so the problem asks you to compute the voltage at the source. So this is the voltage at the source. This is Vs here. The problem asks you to find this Vs. What is the Vs? This is the question A. All right. So everybody knows that when we have the balanced three-phase here, what we normally do in power system is that we are trying to come up with a single phase representation of this. Okay, and what we have to find in this case is that we are trying to find the total the line current here, which is the I line. Okay, what we need to do to solve for this is we need to find the I line first. Okay, and if you have the I line and the other line here, if you use the per phase analysis, there is no current flowing on this path, because we will have the returning circuit as a neutral. Okay, so the way we solve this problem is that we need to write the single phase representation. So let me redraw the single phase representation, or single per phase circuit for this. This is the line. Okay, J2.7 ohms. This is an A point, and of course at this position you need to write with respect to the neutral. Okay, and this is the load. Okay, this is the load. This is the point A prime. Okay, and the voltage at this position is known, because the problem says that the 3810 is line-to-line voltage. So in this case, 3810.5 divided by √3. This is the voltage at the load end. Okay, and of course when the problem says the voltage at any position, okay, the angle it's a reference, so we have to put the angle of 0 here. Okay, okay, the information left for you in order to determine the voltage at the source end is that you need to know, this is the key point, you need to know the line current, which is the I line at this position. So in this case, right, you can see that the I line here is the same as the line current that is flowing in the original circuit. Okay, this is the line current flowing in the three-phase system. Okay, so what you need to see is that the I line here would be the same. If you can find the I line in three-phase. Okay, this is the same current as the current flowing into the single phase system, okay, the single phase circuit, this is the same current. Okay, the problem is, if you may wonder, okay, why is the same? Okay, because in this case we want to have the returning circuit as a neutral, but if you can also do in this way. Okay, you could also put the KVL around this loop, and you compute this straight away from the three-phase system. Of course, by having this the current flowing in this way, you also have, if you put the KVL in this loop, okay, there is a voltage drop across this element, I mean the line of the phase B, so you have to take into account the I line here, which is what? Which is if it is the I line, okay, if I put it as an I line and the angle of theta, okay, in this case you can see that this is this current, right? It is also I line, but the angle, I mean the angle has to be shift by 120 degree. Okay, and you have to take into account this the voltage drop here as well. Okay, this is what that you can that can be done, but it would complicate your calculation a little bit, because you have to get another voltage drop in complex power as well. So I gonna leave this calculation within the three-phase circuit with you for your own study, right? But I will do just for the single phase circuit like this. But you make sure that if you do in that way, and you can compare the result with our calculation here, I would say it should be the same. Okay. Now you can see from here the I line. As I said, the I line or the I load here is the same as the three-phase current. So the thing is that you need to find this I load or I line, which is the load current. Okay, so what you have to see, what you have to use the relationship is that the S load of three-phase is over here. Okay, the voltage drop. So the I load or I line to line is a line current. Here it is the S load, this S load, right? Divided by what? This is a three-phase, and the voltage, the node voltage, is in line to line. So you have to put square root 3 times V, right? V at the load, right? Because the V load here is in three-phase, because in line to line, and you have to put the whole conjugate over here, right? So what you have to do is that you get this S, okay, 660.0704 divided by root 3 times the unit here is in kVA. So kVA, remember that is an angle. Over here the angle of S has to be negative, because the original S load is positive, so negative 36.87 degree, and the V load is since this is the V load is a reference, so the angle is 0, so it doesn't play any role with the phase angle at all, because even you take the conjugation, it doesn't change the angle of 0. Okay. So the V load, of course, must be in line to line voltage. That is 3810.5 volts. But since this is kV, I will put 3.8105 kilo amps. Kilovolts. Sorry, it is in kV. Okay, so the K and the K here cancel, the volt and the volt here cancel, so the remaining part is just amps. All right, so after the calculation, the result of this should be something around 100.011 and the angle of 36.87 m. Okay, or you can say that this is 100 m. Okay, now you get the IL here, so the Vs. Okay, now you can find the VAN or the Vs at here. Okay, at this ascending end, so the Vs here would be you can compute in both in volt or in kilovolts, right? I would prefer things in kV because you know this is in already 3.81 kV. Okay, so I put everything in kV. So this is 3.8105 over root 3 times angle of 0. This is the V at the receiving end plus the current in kiloamp. Now you need to get the current in kiloamp. Okay, because this is 0.1 and angle of negative 36.87. Okay, this is I. The unit of here is kiloamp. You times this by 0.4 plus J, 2.7, right? And make sure this is amp times ohm. So amp times ohm is V, and volt, and you multiply by 1000. This is also in kV. So everything after the calculation, I mean the result of this should be in kilovolt. Okay, so after the calculation you get 2.4017, angle of 4.58 degree kV. Okay, Vs is here. All right. So what you have to notice a little bit is that since the voltage, if you put this, okay, if you check the result a little bit in order to make sure that you understand things. All right. The current is flowing from sending end to the receiving end. That is clear because you know it is the source of energy produced by the generator to the load. So the power has to flow from sending from source to load, right? I mean, in order to allow the current to flow from source to load, the voltage at the sending end must be greater than the voltage at the receiving end. Okay, so you have to you can see from here that the voltage at the Vs here it's greater than this much. Okay, 2.4017 is greater than this guy. Okay, and the reactive power also, you know, you can later we will learn about that. Okay, the reactive power will also flow from the angle, right? You can check reactive power and the power flow direction. Okay, I will just live with this a little bit. Okay, now you can see Vs is in, now the calculation here, Vs is equal to voltage difference between A and the neutral, right? A and the neutral, but A and neutral, since in the problem, right, we don't have any neutral, so it's better to convert this into line to line because we need to compare it with the line to line voltage at the load, right? In order to get the answer for the problem A, you need to answer the magnitude of the line voltage. Okay, the magnitude of the line voltage is easy. If you don't know, if you don't care with the phase angle. Okay, the absolute or the magnitude of the voltage at the sending end in three-phase quantity, so in line to line, okay, in line to line value, so that should be 2.4017 multiplied by root 3, that is 4.16 kV. Okay, this is the answer for 4.16 kV. Okay, if you are interested with the angle, okay, if you want to see the angle as well, so the angle of the line to line voltage will be leading the voltage of the phase of the phase quantity by 30 degree. So that means that the Vs in three phase or in line to line, of course when I put the underscore means it is in complex power. Okay, that should be a complex quantity. Okay, the magnitude is 4.16, angle is that should be the lead of the phase quantity. So you leading by the 30 degree, so you get 34.58 degree in kV. Okay, this is in complex power, complex voltage. Okay, but the problem just asks for the magnitude. Though the problem for question A is this one here, right? So we could answer the question A. The question B would be the real total real and reactive power loss in the line. That is easy, right? You learn from last example 2.7. So the S line here we have three lines basically. So that is that is 3 times. We know the current flowing through each line. So this is an absolute of I line square times the C here it is 0.4 plus J 2.7, right? This is the formula. Okay, now the I line here it's 100. Okay, so you can get 12 plus J 81 kVA. Okay, this is the line. All right, so the problem also asks you this is to answer the question B. Total means this is in three phase. Okay, now the question C, you need to compute the real and reactive power supply at the setting end of the line. You can do in two ways. All right, you could do in two ways. You can compute it straight away from the voltage at the line. Okay, you could compute this directly from the voltage, knowing this voltage and the current. So S as the source would be S at the setting end or source. I put the source, right? S as the source. That is the so in this case the computed Vs. Okay, you could do in two ways. You could do it from the per phase quantity. I mean the single phase quantity, which is here, right? And you know the current IL here. Okay, so meaning that you have three phase balance. So we have the power, equal power for each of the three phases. Okay, so knowing this Vs and IL, Vs times IL conjugate, you get a complex power from the setting end of one phase. Okay, and you multiply this quantity by 3, so you will get the total complex power. Okay, I will do it for you, of course. Let me put it in here. Okay, S at the source in 3 phase, right? That should be 3 times, because it is 3 times higher than the single phase. Okay, Vs is 2.4017, the unit of which is kV. Okay, I put the magnitude first. The IL here is in what, 100 amp. Okay, 100 amps. So in this case it could be 0.1, right? Kilo amp. It's clear. So the multiplication of these two, you get mega VA, MVA, and the angle is what, 4.58, and the angle of this guy of the current has to be conjugated as the conjugation of the IL, because the IL is a lagging. That was a negative 36.87. So after the conjugation, you get 36.87 plus right? This is clear. I hope this is clear. So this is the what you get is 720.51, the angle of 41.45 degree. This is unit of which it's in kVA. I'm sorry, this is in kVA, so you can play around, okay, in kVA. All right. So now let's check the difference. All right. I will just leave this for your own calculation. All right. So you just get the delta S. Okay. If I define the delta S is equal to S of source in three-phase, the difference between the three-phase quantity of complex power at source and the three-phase quantity, the three-phase power of the load three-phase, meaning that this guy negative of, this quantity, okay, is a difference between this guy and the where was it, and this guy, okay, S of the load in three-phase. So the difference between these two numbers highlighted in yellow, okay, you put the two yellow number, they highlighted these two, right? The difference of this, you must get the same figure as the line, the S of the line, which is here, okay. So please make sure that number one, it should be that should be something like this. This is number one. You get number two. So you put 1 minus 2. You should get something close to 12 plus 18. Okay. So number one minus number two. Right, make sure that it should get somewhere around 12, right, point J81 kVA. So that concludes this example. Okay, we'll see you later. Thank you.